Do not copy. Our programs are covered by registered U.S. copyrights. They may not be duplicated or copied. Willful infringement constitutes a felony punishable by fine and imprisonment. Civil remedies include statutory damages of up to $50,000 per offense, plus plaintiff's attorney's fees.
Semiconductors Explained. Part 4. Transistors and Integrated Circuits.
In the last part, you were introduced to several special-purpose diodes, including the Zener diode, the light-emitting diode, the varactor or tuning diode, and the varistor. This part will focus on some remarkable devices that utilize semiconductor technology. One is the transistor. Bipolar and field effect transistors will be examined, along with thyristors. Another device that is based on the semiconductor, the integrated circuit or IC, will be introduced. Let's get started. Many years ago, the vacuum tube was the device used for amplifying weak signals received by radios and televisions.
While it was a landmark achievement in its day, the vacuum tube also had many disadvantages. With the invention of the transistor, the world of electronics was revolutionized. The transistor could not only match the amplifying capabilities of the vacuum tube, but could do so without any of its disadvantages. Transistors are sturdy and last for years, even decades. Because they have no internal filaments, their power requirements are very low. They give off very little heat and take up little space. Most are no larger than your fingernail. Transistors are not only capable of amplifying audio and video signals, but are also widely used in digital circuits as electronic switches. Like other electronic components, a transistor's semiconductor characteristics can be manipulated during manufacture to produce certain results.
The bipolar transistor is one type that is widely used today. It's called bipolar because it requires two polarities of charges in order to operate normally, electrons and holes. Transistors are similar to junction diodes in that they're composed of N-type and P-type semiconductor material. But instead of one p-N junction, a bipolar transistor has two junctions. It's composed of a single semiconductor crystal with three different areas. The center part is called the base. This narrow region can be made of either P or N-type material. The two outer areas, known as the emitter and the collector, are composed of the opposite type of semiconductor material. Notice that the collector is the larger of the two. Bipolar transistors can be either PNP devices or NPN devices. We'll focus primarily on the more common NPN transistors. Besides the differences in physical size, there are also differences in the doping levels of each area. The emitter is the most heavily doped. The base region is the most lightly doped. The doping level of the collector falls somewhere between the two. This is true for both NPN and PNP transistors.
Here is the schematic symbol for the NPN transistor. Notice that there is an arrow on the emitter lead. The same is true for the PNP schematic symbol, but the arrow points in the opposite direction. The arrow in either symbol always points from P to N material. This will help you identify the symbols.
Before you can understand how a bipolar transistor will behave with an applied voltage, you need to have a sense of how it will respond in an unbiased state. Here's an analogy that may help. A bipolar transistor is structurally similar to two back-to-back diodes because of its two p-n junctions.
As with any p-n junction, there will be a natural diffusion of charges across them. two depletion regions are created, which are devoid of any electric charges.
Let's review how the depletion regions are formed. At the emitter-base junction, some of the electrons in the N material diffuse and recombine with holes in the P material of the base. This forms columns of ionized atoms. This same process occurs at the collector-base junction, forming a second depletion region. The oppositely charged ions on either side of the two junctions create a barrier potential across each. Once again, for a silicon transistor, the value of this potential is about 7/10 of a volt. Keep in mind that similar processes occur in the PNP bipolar transistor as well.
Now let's see how an NPN transistor reacts to applied voltage. An important rule of thumb in transistor operation is that the emitter-based junction is always forward biased and the collector-based junction is always reversed biased. Let's see why.
This is where it's helpful to think of a transistor as two back-to-back diodes. In order to forward bias the emitter-base junction of an NPN transistor, the P-type base must be more positive than the N-type emitter. Conversely, to reverse bias the collector-base junction, the P-type base must be more negative than the N-type collector. These requirements are fulfilled by connecting the emitter and collector supply voltages with the polarities shown here.
Let's take a closer look at how current flows through a bipolar NPN transistor.
The negative voltage on the N-type emitter forward biases the emitter-base junction. Because of this, the depletion region narrows and disappears, allowing current to flow easily through the emitter and into the base. The positive voltage on the N-type collector reverse biases the collector-base junction. Remember that when reverse biased, the depletion region becomes wider, but something unexpected happens at this point. While a wider depletion region usually behaves like an insulator, blocking current flow, in this case, current will flow into the collector. In fact, most of the electrons, 95% of them, flow through the base and into the collector. Let's see why this happens.
Remember that the base region is extremely thin and very lightly doped. So, while the heavily doped emitter has an abundance of the majority carrier free electrons in the case of an NPN transistor, the very lightly doped base has only a few majority holes with which the electrons can recombine. Those that do pair off will flow out the base lead and into the external circuit. This completes the current path that's necessary to eliminate the depletion region of the emitter-base junction, along with its barrier potential. Because there are so few holes in the thin base region, most of the electrons that flow through the base are propelled into the collector. Once there, these electrons drawn by the positive potential will flow out of the collector and back to the source.
Here's the schematic symbol for the NPN bipolar transistor in the circuit. Be sure you remember which lines represent the emitter, the base, and the collector. An important thing to realize, however, is that there are two different voltage needs. Look at this variation on the circuit. Resistors are used in both the base and collector circuits to set the currents to the desired values. The magnitude of the voltage source on the emitter only has to be high enough to overcome the barrier potential and forward bias the emitter-base junction, 7/10 of a volt for silicon. The collector voltage, on the other hand, is usually much higher because it must provide enough attractive force to draw the electrons through a reverse bias junction and into the collector. In reality, a single voltage source can be used to satisfy both criteria, which you can see connected to this basic transistor circuit.
The relationship among the various currents that flow through the transistor is an important one and can be represented mathematically with this formula.
The emitter current, I sub E, equals the base current, I sub B, plus the collector current, I sub C. As long as any two variables are known, the third can be easily determined. For example, if you know that the emitter current is 20 milliamps and the base current is 100 microamps or 0.1 milliamps, you can easily calculate that the collector current is 19.9 milliamps. This level of collector current represents 97.5% of the total emitter current.
In addition to the bipolar class of transistors, another major group is field effect transistors. Compared with the bipolar devices, which require two types of charges, holes and electrons, field effect transistors depend on just one type of charge, holes or electrons. Because of this, they are referred to as unipolar devices. There are two major types of field effect transistors. One type is known as the junction field effect transistor, or JFET. The other is called the metal oxide semiconductor field effect transistor, or MOSFET.
Let's look at the JFET. Here is the schematic symbol. Notice that it has three leads: the source, the gate, and the drain. In terms of their semiconductor composition, JFETs are manufactured as either N-channel or P-channel devices. Just as with the bipolar schematic symbol, the arrow always points to the N material. Let's look closely at an N-channel device. The foundation or substrate is made of N-type semiconductor material, into which are embedded two regions of P material. The drain and source leads are connected to either end of the N-channel, while the gate is connected internally to both of the P regions.
Here is the JFET in a simple circuit. There is the normal diffusion of charges across each PN junction, resulting in the formation of two depletion regions. The way that the JFET is biased is very different from that of the bipolar transistor. While the emitter-base junction of the bipolar transistor was forward biased, the gate source junction of the JFET must be reverse biased, as shown here. This means that aside from a small reverse current, there is no gate source current. Current flow through the N-channel JFET is established by a positive supply voltage that is connected between the drain and the source. The magnitude of this current is controlled by the reverse voltage that is applied to the gate. Remember, no current flows through the gate circuit because the gate source junction is reverse biased. This means that as the gate voltage is increased negatively, the strength of the reverse bias also increases, which in turn causes the depletion regions to become wider. As this happens, the channel through which current can flow becomes narrower, so the current flow decreases. The value of gate voltage that causes the depletion regions to block the flow of current is called the cutoff voltage. So as the gate voltage becomes more negative, the current through the JFET decreases. This means that current through the JFET is actually at its maximum when the gate voltage is 0.
Let's look at another unipolar device, the MOSFET. Like the JFET, the MOSFET has three leads: the drain, gate, and source, labeled D, G, and S, respectively. The main difference is that the gate is electrically insulated from the current channel by a thin layer of glassy material called silicon dioxide. Because of this insulating layer, a controlling gate voltage of either positive or negative polarity can be applied without producing any gate current.
There are two main types of MOSFETs, depletion mode and enhancement mode. For both types, there are N-channel and P-channel configurations. Here's the schematic symbol for the N-channel depletion mode MOSFET. Let's look at a sample circuit that uses one. Just as with the JFET, the function of the drain source voltage is to establish the flow of current through the transistor, while the gate source voltage is used to control the magnitude of the current. When the gate voltage is 0, current can flow through the narrow channel. As the gate voltage is increased negatively, the depletion region widens, which causes the current to decrease. When the negative gate voltage reaches a certain level, current through the channel is completely blocked. In these respects, the depletion mode MOSFET is very much like the JFET, but unlike the JFET, the polarity of the gate voltage can be reversed without producing any gate current.
While the depletion mode MOSFET is very useful in certain applications, the enhancement mode MOSFET is the device that has revolutionized the electronics industry, particularly in the area of digital electronics and computers. Let's take a look at its basic operating features.
Once again, there are both N-channel and P-channel types. Here's a graphic representation of an N-channel enhancement mode MOSFET. The usual biasing voltages consist of the drain and gate voltage supplies. Notice that there's no current channel initially. Let's see how it works. The positive potential that is applied to the gate draws electrons through the P material toward the gate. Because it's insulated, however, the electrons can't flow into it. Instead, they accumulate at the gate and form a thin layer that acts like N material. When this layer is created, a conductive channel is formed through which current is able to flow. Notice that while there was a current path through both the JFET and the depletion mode MOSFET even when gate voltage was 0, the gate voltage for the enhancement mode MOSFET must be high enough to create the conductive channel. That is, with 0 gate voltage, current cannot flow. One word of caution about MOSFETs. The thin insulating layer of silicon dioxide can be easily ruptured with any type of transient voltages, including static electricity.
Besides the bipolar and field effect types of transistors, another important group is thyristors. Thyristors are used as control devices to either pass or block electrical flow to or from certain other devices, such as motor and heating units. A common type of thyristor is the silicon-controlled rectifier, or SCR. The SCR is a 4-layer semiconductor device that can be switched back and forth between conducting and non-conducting modes, so it's used to control electric current. The SCR is composed of alternating layers of P and N material. The 3 leads are identified as the anode, the gate, and the cathode. The semiconductor structure of the SCR simulates 2 interconnected bipolar transistors, one PNP and the other NPN. Here is an equivalent circuit for an SCR using 2 bipolar transistors. In order for the SCR to be switched on, a triggering pulse must be applied to the gate. What makes the SCR so unique is that because of the feedback loop that is developed between the 2 transistors, the SCR will continue to conduct even after the gate voltage is removed. Here is a schematic symbol for the SCR. It's referred to as a unidirectional device because it conducts current in only one direction.
You've now been introduced to important aspects of several different types of transistors, all of which are based on semiconductor theory. The transistor has led to other significant inventions, most notably the integrated circuit, which also utilizes semiconductor principles.
The development of microelectronic technology has made it possible to put many electronic components, such as transistors, diodes, resistors, and capacitors, on a single silicon chip. This is called an integrated circuit, or IC. Inside an IC, hundreds or even thousands of components are etched into the silicon, which is embedded in the body of the IC.
Let's see how IC technology depends on basic semiconductor theory.
An IC is composed of alternating layers of P and N material, as you can see in this graphic cross-section. By etching into or through the surfaces of 1, 2, or several layers of doped regions, minute components can be made. For example, a diode can be formed by layering first N material and then P material on top of a P-type substrate, which is used as a foundation. Tiny holes or windows are etched into the upper and middle regions through which a small amount of metal can be deposited to provide the necessary electrical contacts. By adding another layer of N material, an integrated transistor can be formed in similar fashion. Even the most complex circuit is simply a matter of layering P and N materials, etching windows, and interconnecting the fabricated components.
Remember, the operating principles of the layered semiconductor regions within the IC are identical to those basic concepts examined in this series. Let's stop here and review.
In this part, you have examined several common types of transistors in detail.
You were also introduced to the semiconductor aspects of integrated circuits.
All of the semiconductor devices that have been presented in this series affect your daily life, from the way you work to the way you spend your leisure time. A great deal of material was covered. View this series again if you have any questions.